The subject of differential equations is a pretty broad subject, and it's an application of integration. Most undergraduate programs offer 1, 2, or maybe even more courses in the subject. In most Calculus 2 classes, however, usually it's just a single chapter that's devoted to the topic. So what is a differential equation? Well, an equation, remember, is just a relationship between two expressions. So a differential equation is an equation that involves expressions involving differentials. Okay, well, so that would include x, and it would include y, which sometimes might be represented as f of x, but then it would include derivatives, second derivatives, third derivatives, and so forth. The solutions to differential equations are actually functions, and they're functions that, when substituted into the differential equation, make the equation true. Now, before we get into differential equations, I want to think about another type of equation that you've probably encountered. We want to verify that x equals -3 is a solution to x squared equals 2x plus 15. Okay, and I do want you to bear with me just so you can kind of think about exactly what's going on. Well, some industrious students would say, okay, I know what I have to do. This is a quadratic, so I have to get all the terms on one side of the equation, I've got to factor, and then I've got to do all this. Yes, that's true. You can do that. However, all we're doing is verifying that it's a solution. It will be a solution if, when we substitute -3 into the different values of x, we'll get the same thing on both sides. And so I prefer to have it so that we do exactly that. We just say, well, I've got x squared, and I've got 2x plus 15. When x is equal to -3, we end up with -3 squared, which is 9. On the right side, we end up with 2 times -3 plus 15, which is also 9. Since these are equal, x equals -3 is a solution. That's awesome, okay? And that's because they're equal. Now, there is another solution to this, of course. I'm guessing, what is it, +5. You would get 25 on the left side and on the right side. But we're not asked to find the solutions. We're just asked to verify something is a solution. So when you're asked to verify if something is a solution, figure out what derivatives you need, firsts, seconds, fifths, whatever they may be. Substitute those into the equation and substitute your function in for y. I really insist with my students, just take each side of the equation separately. So notice how we kind of put a little divide here between the x squared and the 2x plus 15. Don't start off by saying they're equal, because you're testing if they're equal. You get to the end and you're like, oh yes, 9 equals 9. That's not terribly surprising. Okay, so do it separately. That's my suggestion. In our first example, we're going to look at the differential equation dp dt equals 0.02p. This is a special type of differential equation known as exponential growth. And the reason it's exponential growth is because we have a function p, and the rate at which p is changing is proportional to p, which means it's a constant multiple of p. That's typical of an exponential growth type of equation. So we're going to show that p equals 400 times e to the 0.02t is a solution to that differential equation. Okay, so what I'm going to observe is that on the left side, I have dp dt. That's the expression on the left side. The expression on the right side is 0.02 times p. In order to verify this, I need to figure out what the derivative is of p with respect to t. So we'll take our equation here, and we'll find its derivative. We'll do this off to the side. dp dt is equal to, well, it would be 400, because it's a constant multiple, times e to the 0.02t, and I ran out of room there, but we would have to multiply by the derivative of the exponent, and the derivative of 0.02t is going to be 0.02. So I'm going to multiply that down there. Sorry about that. And if you multiply 0.02 by 400, you end up with 8 e to the 0.02t. Okay, so I've actually done all the work over here. dp dt is 8 times e to the 0.02t. Okay, now we're going to set up a little bridge there, a wall that is, I guess. We want to make sure that the other side of the equation, 0.02 times p, is equal to the same thing. Well, we know what p is. P is equal to 400 times all that business. So we end up with 0.02 times 400 e to the 0.02t, and these calculations will seem familiar. 0.02 times 400 is 8 e to the 0.02t. Okay? And so we say they're equal. dp dt is equal to 8 times e to the 0.02t. I'm sorry, not that. It's equal to 0.02 times p, because these two expressions are equal. Let's look at another example now. Now we have a different differential equation. This time it's y as a function of x, dy dx. The rate dy dx is inversely proportional to the function y. What do we mean by inversely proportional? It means it's a constant multiple of the reciprocal of y. So it's 4 divided by y. We want to show that this particular function, radical 8x plus 81, is a solution to the differential equation. So once again, we'll put up a little border here between them. On the one hand, we need to calculate dy dx. And on the other hand, we need to calculate 4 divided by y. Okay, well, our function, y, is really 8x plus 81 to the 1/2 power. So in order to find dy dx, we would take the derivative, which will be 1/2 times 8x plus 81 to the negative 1/2 power. And then the chain rule dictates that we multiply by the derivative of the inside, which would just be 8. And now things seem to be coming together. The 8 multiplied by the 1/2 will give us 4. So we end up with 4 times 8x plus 81 to the negative 1/2. Okay, so that's the left side. That's what dy dx looks like. Now let's look what 4 divided by y looks like. Well, that would be 4 divided by the square root of y, well, divided by y, which is the square root of 8x plus 81. Now, at first glance, of course, these two don't look identical to each other, but if we interpret the exponent of negative 1/2, the negative one says send me to the denominator, so it's going to be 4 over this stuff, and then the 1/2 power says take the square root. And we see once again that our values are equal. The left side of the equation and the right side of the equation are equal, and so that is a solution to the differential equation. Another one, okay, this one's a little simpler, and I don't think it's necessary really to calculate both sides, since one of the sides of the equation is equal to 0. But we want to show that sine y equals the sine of t satisfies the differential equation where we take the second derivative of y, add to it 4 times y, and we should end up with 0. So let's over here on the side figure out what the first derivative and then the second derivative will be. We're going to use the chain rule. The derivative of the sine of 2t, so dy dt, is going to be the sine of, or the cosine of 2t. Derivative of the sine of an argument is the cosine of that argument, and then we need to multiply by the derivative of 2t, which I'll put out front as positive 2 there. We want the second derivative. In order to get the second derivative, we take the derivative of the cosine of 2t, which will be negative sine of 2t. And just as before, we need to use the chain rule. Take the derivative of 2t, which once again is 2. When we multiply it by the 2 that's already the coefficient, it becomes negative 4 times the sine of t. So let's take that left side of the equation, the second derivative of y with respect to t, plus 4 times y. Well, we just calculated what the second derivative is. It is negative 4 sine of 2t. And then we want to multiply 4 by y. Well, y was the sine of 2t, and it's very clear to see that this is going to be equal to 0. For our next one, example 4 here, sometimes e to the kt, y equals e to the kt, will be a solution to this. We call this a second order differential equation. Why is it a second order differential equation? It's a second order differential equation because the highest derivative that appears is the second derivative. Okay, so we're assuming that e to the kt satisfies the differential equation, and so I need to figure out what k is. Let's figure out what the derivative and the second derivative are. So y is equal to e to the kt. Y prime will be, we take the derivative of e to the kt, which is e to the kt, but we multiply that by the derivative of the exponent, which is k. On the other hand, y double prime, we're going to take the derivative of e to the kt. Again, there's already a k in front. When we take the derivative of e to the kt the second time, we get an extra factor of k, so it's going to become k squared. Again, that's the chain rule taking over for us. Now, we know that this is a solution for some values of k, so let's figure out what those are. So let's start off with the equation y double prime equals, what is it supposed to equal? Y prime plus 2y. And substitute all this stuff in. Y double prime is k squared e to the kt. Y prime is k e to the kt. And 2y is just going to be 2 e to the kt. Okay, there are certain values of k that will make this equation true. In order to figure out what those are, let's study the equation. Well, I noticed that every single term in the equation has an e to the kt in it. So let's get all of the terms on one side of the equation. We'll have k squared e to the kt minus k e to the kt minus 2e to the kt equals 0. Factor out e to the kt. That's why we did this. We brought them over because the e to the kt is in common with all of them. That leaves us with k squared minus k minus 2. That's equal to 0. All right, when we have two things multiplied together and we get 0, one of them has to be 0. Well, that would mean that one of the possibilities is that e to the kt equals 0. However, e to the kt is an exponential growth function or possibly an exponential decay function should k be negative. In both circumstances, e to the kt is positive, so it can't be 0, and so that provides no solutions. Okay, so we'll take the k squared minus k minus 2 and set that equal to 0. Here we have a quadratic. When we want to solve a quadratic equation, we factor. This factors as k minus 2 times k plus 1 equals 0. Now we have a product of two things equaling 0 again, so k minus 2 should be 0, which means k would be 2, or k plus 1 would be 0, which means k is negative 1. So these are the two values of k for which y equals e to the kt will be a solution. I'm going to give you a bonus piece of information here. Here's the bonus piece of information. If we take these two values, 2 and negative 1, we could create a new equation, which is y equals e to the 2t, right? It's e to the kt, plus e to the negative t, negative 1 times t that is. And that also will be a solution. In fact, if we go ahead and throw constants in front of those, let's say an a and a b, that will also be a solution. If you take a course in differential equations, you'll learn how to solve these types of differential equations, and you'll also be given a some sort of initial value. So maybe y at 0 and y at 1, or maybe y at 0 and y prime at 0. And that will allow you to figure out what the constants a and b are for those particular what we call initial conditions. For our next example, we're going to once again find constants that will make a function a particular solution of a differential equation. So here we have y equals c x to the n, and it should be a solution to x times the derivative of y with respect to x minus 3y equals 0. So I see from this differential equation that I need to figure out what dy dx is. So we're going to take the derivative. Well, because it's c times x to the n, the derivative will be cn x to the n minus 1. Let's put this into the equation. It's supposed to be equal to 0, so x times the derivative, which is c times n x to the n minus 1, minus 3 times y. Oh, well, y, oops, that should be y prime over here. Y is equal to c times x to the n. This should be equal to 0 when I'm done. We can do a little bit of a simplification here. First of all, let's multiply the x by the x to the n minus 1. We'll get cn x to the n minus 3c x to the n equals 0. I need to figure out what values of c and n will make this a solution. Let's factor out, let's see, what do we have to factor out? We could factor out a c, that's in common to both terms. X to the n is also in common to both terms. And when we factor that out, we'll be left with an n from the first term and a minus 3 from the second term. We want to know when that's 0. When we have a product of a bunch of factors equals 0, then one of those factors must be 0. So c could be 0, x to the n could be 0. There's an issue with that, which we'll discuss in a second. Or n minus 3 could be 0. Okay, let's start with this last one. If n minus 3 equals 0, that means n is equal to 3. N is a constant. Now we could also have c equal to 0, and that's really darned boring. Because if c equals 0, let's look at the original function. Y is equal to c times x to the n. Oh, well, that would mean that the function is 0 itself. That's not terribly exciting. However, the one in the middle here, the x to the n equals 0, keep in mind that x is a variable. We want to know which values of n would make this 0. Well, the exponent can't do it. The only value of x that would make it 0 is when x is equal to 0. And since x can vary, it will not be fixed at 0. So that middle term there just defines for us no solutions. It doesn't give us any solutions. Okay. So the next thing that we're going to discuss is what an equilibrium solution. Okay, remember that a solution, when we're talking about a solution to a differential equation, we're talking about a function y equals f of x. So a solution to a differential equation will be an equilibrium solution if the rate at which y is changing is 0, so the derivative is 0. Something is at equilibrium if it's unchanging. And that's why we say this is an equilibrium solution, because the derivative is equal to 0. Now, what does that mean? Well, remember we're dealing with functions, okay? So I'm going to draw a couple of functions. Here's a function. Bloop. That's a function. Is that derivative equal to 0? Well, of course not. There are spots when the tangent lines are positive, so the derivative isn't equal to 0 all the time. Well, let's look at another function. How about this guy? Is that guy's derivative equal to 0? No, because there are tangent lines that are non-horizontal. Oh, in order for a derivative to be 0, the tangent lines have to be horizontal. So this is a potential function that could be a solution that would be an equilibrium solution because the derivative of y with respect to x is 0. The line has a slope of 0. When we're looking for equilibrium solutions, we're looking to see when the derivative is 0. So let's look at for the equilibrium solutions to dy dx equals this particular monstrosity. Okay, this one's a bit challenging and you have to use some algebra stuff that you may have forgotten a long time ago. An equilibrium solution is a solution for which this stuff will be, the derivative will be 0. So we want dy dx to be 0, which means all of this stuff should be equal to 0. So let's create an equation that says that x times y minus plus 4 times y minus 2 times x minus 8, we want that to be 0. I need a function. I need a function y equals f of x that makes this 0. Well, I'm starting to see some troubles here. Let's see here. I don't know what to do. Well, let's just take a look at the first two terms. What do I notice is similar about them? Oh, well, they each have a y in them. So let's just mess around with that. Let's factor out a y from that. We'll end up with x plus 4. How about those next two terms? Well, they certainly have a 2 in common with them, and they're both negative. So maybe I should factor out a minus 2, a negative 2. Well, that would leave me with, from the first term, we would have a plus x, and from the second term, that minus will change into a plus. It'll become plus 4. Oh, so now I see this common factor of x plus 4 in both of those. And so we can factor that out, which will leave us with y minus 2 times x plus 4 equals 0. So that either means that y minus 2 equals 0 or x plus 4 equals 0. Now this last one would tell me that x is negative 4. The first one tells me that y is equal to 2. All right, before we declare our answer, we need to think about what it means to be an equilibrium solution. A solution is an equilibrium solution if it's a function for which the derivative is 0. Functions are of the form y equals, which rules out x equals negative 4. X equals negative 4 isn't a function where y is a function of x. However, y equals 2 will be a solution. So that will be our equilibrium solution for this particular problem. One final example. Which of the following graphs cannot be a solution to this differential equation? Y prime equals x divided by y. Y prime equals x divided by y. Well, wait a minute. What is going on here? What do we mean by that? Well, y prime, let's think about that. Y prime is the derivative. So this is saying if you give me an ordered pair xy that's on the graph. So x comma y will be on the graph of y equals f of x. If you give me that particular ordered pair, then x divided by y should be equal to the slope of the curve at that particular point, or the slope of the tangent line. Okay, so let's take a look at the very last one, because I see that's a kind of a nice little line there. Let's pick a point. Let's pick the point. Well, let's not do 0, 0, because that's a little bit goofy. How about the point, oh, that's very small to see, but that's the point 2 comma negative 2. If I divide x by y, 2 divided by negative 2, I end up with negative 1. Is that what the slope is there? Well, let's see. The slope at that, well, this is a linear function. The slope is always negative 1, isn't it? We're going down, like here we go down 2 and over 1, or down 2 and over 2. So it'd be a slope of negative 2 rise over 2 run. Yeah, that seems to be right. Wait a minute. How about this point? This was the point negative 1 comma 1. If I divide x by y, do I get negative 1? Well, of course I do. Negative 1 divided by 1 will be negative 1. The slope is negative 1 once again. Okay, why is that important? Because the slope of this entire line is negative 1, and regardless of whatever point we pick on it, we get a slope of negative 1. Okay, so I hope that makes some sense. Let's look now at something over here. How about this guy? That's a nice ordered pair to pick out. The x value is 0. The y value is about 1 point something-ish. And the tangent line has a slope of 0. Well, if we do x over y, we get 0 over 1.6, which is equal to 0. The slope of the tangent line is 0 there, so that seems to work. Over here, this is more challenging. There x is equal to 2, y is equal to about 2.5. If I do x divided by y, I get 2 divided by 2.5, which is equal to 0.8. This slope seemed like it's 0.8. That's possible. If I do the same thing on the other side, it's probably about negative 0.8 there. Yeah, and that would be negative 2 comma 2.5. So that seems reasonable. Okay, let's go for this guy in the third position. Here we have an ordered pair where x is 0, y is 2. If I do x divided by y, my x value is 0, my y value is 2, I get 0. Is the slope of the curve equal to 0 at that particular point? Well, no, it isn't. It's a line, and the slope is the rise over run, which in this case is 1. Okay, so here the slope and x over y do not match. So the graph that is not a solution is this guy right here.